In this lecture, we are actually going to see CUDA programs. So typically for today's lecture, we'll be seeing looking into the various. So we'll first look into HelloWorld program, and we'll also see its different variations. At the end, we'll also see. We'll also see how actually we can execute the CUDA program with multiple number of threads, and how can we allocate memory on GPU and all those stuffs. So that's a quite brief outline for today's course, today's lecture. And yeah, so with this, let's get started. And yeah, as I tell in each and every lecture, if you have any doubts, please feel free to ask during lecture or after lecture, or at the end of the lecture, or you can also post them on Google group. Any of the way is the way you are convenient with. Uh, so yeah, so let's get started. So agenda for next 3 classes is going to be computation. So in this, as I probably told in previous lecture also, we'll be seeing various small codes, CUDA codes. We'll also see how the data transfer occurs between CPU and GPU, and we'll look into the thread hierarchy. We'll see what is work, what is thread blocks, and all those things. So that's going to be the agenda for our next 3 lectures, which is also known as computational aspects of GPU or CUDA. Then we'll see memory synchronization. In memory we'll see different hierarchies in GPU memory, and we'll see what is different types of memories, like how can you use the GPU cache and shared memory and all those stuff. So we'll also see what's coalescing and all those things. Okay, and then we'll look into synchronization. So how threads, when we have multiple number of threads running concurrently, at the same time, and what synchronization issues we face, and like data races and all those, and how do we handle them, which we'll see later. Then we'll see function supports and topics. Okay, so for today's lecture, we're going to see look into the computation aspect, and yeah, so let's get started with it. uh, so this is the typical a very simple hello world program which is written in C. There is nothing related to GPU or CUDA in this. And as we know, the output of this program is hello world if we run it using a GCC compiler. So if we type GCC hello world.c, assuming that hello-world.c is the name of that C program, and we run /a.out, and we'll see hello world on our screen. Yeah, so that's it. And so one thing to note here is that okay, now we want to run this using not GCC but NVCC compiler, which is the CUDA compiler. So we run this using NVCC hello.cu, and we do /a.out. And one thing you will notice is that this program will run fine and will also give the correct result as it does with GCC. So the point to observe here is that GCC is, the codes that you will be able to run with GCC, you will also be able to run with NVCC. And yeah, so that's like, NVCC, you will be able to see run C as well as, C plus CUDA programs. And yeah, that's fine. But as I told, there is nothing related to GPU here, or we are not at all using, not at all doing parallel computing or anything related to the GPU in this code. So, this is not good. We are not doing GPU programming at all. So we would like to move on and see the GPU hello world. So how a typical GPU hello world program would look like. So this is what it looks like. So here you would observe many similarities, but there are 3 key differences. First is the header file that you will see, hash include CUDA.h, uh, which is the header file that you need to include each time when you want to write, when you want to write the CUDA code. And it will contain the necessary functions for the CUDA related CUDA related functions and all those things. And so that's the first thing. Second key thing here is that you need to include __ global __ in front of the function, which is also, which is declared as, it's named as t kernel. So what this underscore 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 global underscore underscore tells you that this function void, I mean, which is named as t kernel, is not a normal function. It is a GPU kernel. So what is GPU kernel? GPU kernel is a function which is executed on GPU. It's not a normal function. It will be executed on GPU. And yeah, it, I mean, this word will differentiate it from the normal function. And rest things you can see that, that those are same as CPU, I mean CPU or C function that you declare. There is a return type, then there is identifier, which is the name of the function, and then there is this braces in which you can specify the parameters to the function call. And then curly braces begins, and then you write the body of the function and so on. But the key thing is this global keyword, which differentiates it from the normal CPU function, and it tells compiler or NVCC compiler that it's a GPU function or the kernel which will execute on GPU. So that is the second difference. The third thing that you should observe is the call to the kernel or the GPU function, which is also much similar to the normal function call in C. But the typical difference that you will see here is that there is this triple less than and triple less than, then 1 comma 1, then triple greater than in between this. So this is the name of the function that we want to call. Then the argument list is as it is. Here we will specify arguments, if any, which will be passed to the GPU function. But this thing, this triple less than 1 comma 1 and triple greater than, this tells GPU that I want to launch this kernel or this GPU function with 1 into 1 thread, which is single thread, and yeah, it will launch. I mean, it will launch the kernel with just one thread. Uh, okay, so moving on. So as I told, this part is known as kernel, which is executed on GPU, and this is called as kernel launch. And with how many threads it is launched, it depends upon these two parameters. In this case, 1 comma 1 states that we are launching kernel with 1 into 1 thread. Okay, so okay, I'll stop here for a moment and see if there are any questions. Basic questions. Yeah, come back to slides again. Yeah, attendance thing I already. You don't need to do present and all those things. I mean, WebEx. Sorry, this Teams already takes care of it. I think someone is. I mean, voice is coming from someone. If everyone can mute, it will be helpful. Okay, someone is saying that I cannot. I mean, I cannot able to see the screen. I mean, was everybody able to see my screen or hello? Can someone
Yes, sir.
confirm?
Yes, sir, it was visible.
Yes, sir.
Okay, okay.
It's
Yes,
visual,
sir.
sir.
Yeah, okay. Thank you. Yeah, thank you. Why is 1 comma 1 for one thread?
Hello.
Yes, go
Hello,
ahead.
sir. Actually, I'm not able to see the meeting chat in my group. Can you please help me in this?
Uh,
Same here, sir.
Sorry.
Same here. I can see the chat.
Yes,
Oh,
sir. I'm not able to see the chat here.
okay. But chat must be. I mean, it's nothing private. I mean, it's open to everyone. Is it something? I mean, some
Actually, I
that.
think I'm not adding in this group so that I'm facing this problem, I guess. In meeting group, I think I'm not adding.
Actually, there is no need. I mean, I haven't added anyone actually. I have kept this meeting sort of open to everyone, and yeah. So
Using mobile, that could be a reason. So using mobile means look at the top right. There should be a banner with the name of the course, and that should be up there.
sorry. Can you repeat? Hello.
Yeah, if I'm using mobile, the chat would be in the top banner. You have to touch the screen, and it will be next to the course name.
Okay.
Yeah, I
So
guess
actually,
that should.
I'm using the laptop, but I didn't see any of these options. Yeah, I know it's bottom or top of the mobile or laptop, but I didn't get.
It should be beside the raise hand option, but there is no chat option right there.
That's strange because I don't think that, I mean, at least from my end, I haven't disabled anything. So it might be some issue with Teams or something, I guess. But
Maybe, sir.
yeah, because if everyone, I mean, most of the people are able to see, then at least, I mean, uh, it's not like something which is disabled from my end.
Mhm.
But okay, I'll look into it after the lecture, because
Right,
right
sir.
now, I
Thank you,
mean,
sir.
we are running out of time
Sure,
and
sir.
I need
Thank
to
you.
cover a lot of content. That's why I'm telling.
Okay, right, sir. Thank you, sir.
Okay. Why is 1, 1 for one thread? Yeah, because 1, 1 means we are launching kernel with 1 into 1 thread. Think of it like uh, there are uh, there is one class inside which there is one student. So 1 into 1 mean, I mean, uh, left one denotes the class number of class, and right one denotes the number of students. In this way, here left one denotes some block and right one denotes the number of threads in that block. So 1 into 1 thread. What do the first one and second one signifies? I already explained in the previous question. Sir, what is NVCC? NVCC is the compiler for compiling the CUDA programs. Hello, sir. How to add number of GPUs in kernel for number of GPUs in kernel call? Uh, Actually, I mean, this is quite an advanced thing. I mean, we will talk about how to deal with multiple GPUs, but for now, let's focus on one GPU. And in fact, we need to first of all look how can we run the code with multiple threads. Sorry, two parameters. Yeah, I mean, you can pass the parameters in that function itself. We'll see later. I mean, I have an example for that. So don't worry about it. I think you can reload the page. Press third button for, okay. What is kernel? Kernel is something which is, I mean, it's like a normal function, but think of it as a GPU function. I mean, something that is executed on GPU, function that is executed on GPU. Can you explain a little more about NVCC and GCC?
Sir,
Yeah. Yeah, go
I
ahead.
have one question regarding to this. Actually, the thing that you applied in C language can be applied in any of language, means that you applied in kernel, that after that kernel function, means any of the language the same process will be held
Okay, so you are asking can
in
we
Python
declare
same.
kernel same way in different languages as we did in C? I
Yeah,
guess
means
you will
the
need.
process will
Sorry, yeah, go ahead.
the yeah means just suppose if I say that in Python, can we apply the same thing that we applied in the C language, means to
Yeah,
declare the
actually,
kernel and
I understood. Yeah, I understood. Like, actually, for Python, I think you will need a different compiler. NVCC is C plus CUDA. Think of it like that. But for Python, I think compiler is different, and you need to look for it. Uh, so yeah, but I don't think that same thing you can apply for Python also. It will be slightly different, is what I
okay.
think, because the compiler won't be the same. Yeah. Sir, where can we practice CUDA? Don't worry. I mean, we have a lot of codes here, and just in case you need practice question, I can also give you later. Uh, Sir, for CUDA programming, which software we have to download? NVCC. I mean, that's the CUDA compiler. And is it necessary for GPU function to have name dkernel, or we can any other? Okay, yeah. So dkernel is just an identifier. You can give any name. You can also give your name to that kernel. It won't affect, as long as you are adding that underscore global underscore. It the name won't matter. It can be dkernel or something else. So yeah, this is a very important point, and yeah, please keep note of that. I mean, name of the function is not important. You can change the name, but yeah, that global is important. That specifies that it's a GPU kernel.
Yes,
Okay,
sir.
so going on, yeah.
Yes, sir. Are we going to learn PyCUDA also?
As I told in previous lecture, we won't be learning PyCUDA. We'll be learning the C. I mean C plus CUDA.
Mhm.
But you can uh, explore it in your own time. I mean, concepts wise, both the things will be same, but yeah, the syntax wise it will be different.
Okay, sir.
And yeah, for this course it will be NVCC, which is very much similar to C. And yeah, Python is quite, I mean, the compiler is different, and yeah, we won't be covering that in this course.
Okay, sir. Thank you.
Sir,
Yeah, go ahead.
yeah, I have a doubt. Can I know why we have to inculcate a different function, a void function for declaring the kernel and then the kernel launch separately? Why don't we bring it all together in a main function?
Okay, so like, in order to execute something on GPU, I mean, you need to tell that, okay, this is the portion which is being executed by GPU to, I mean, to the CPU. I mean, CPU is the essentially the one who will be offloading that function to the GPU. And in order to do that, you need a very clean way to do. And it seems like writing a function and marking it using global is a very modular way of doing it, and hence we are doing it.
Okay, sir. Thank you so much.
Okay, I'll come back to questions after it, or probably is it necessary for GPU to have? Yeah, I took that question. What is the function doing there? It's a GPU kernel. Okay, we'll learn more about it. But yeah,
Sir,
yeah.
Actually, GPU, actually in GPU, the GNU like Octane is like a software using to execute now, sir. Here, what is the software using, sir?
I mean, it's NVCC compiler. You can download that compiler. I didn't understood the question. I mean, you are compiling this code using NVCC compiler.
sir,
Okay, yeah, go ahead.
sir, how many threads are available in NVCC, sir?
Okay, that depends upon the GPU, and in fact, we can launch. I mean, millions of threads, but yeah, we'll come to it. That the limit with which we can launch the kernel is actually very high. But in coming lectures, we'll see. But please don't worry about it right now. So yeah, that's I would say, right. Yeah, so switching back to slides because I want to cover a lot of things. So yeah. Okay. So yeah, we saw this. Now, when we compile this code with, I mean, code using NVCC hello.co and run./a.out, we see something strange. We won't be able to get any output. So this is quite strange, and we would like to know why is it happening. And the reason is this, that when okay, so let's understand what is happening here. So CPU starts executing from main. It sees that there is this instruction which is a kernel call. So it launches the kernel call and it moves ahead. And okay, so it launches the kernel and move ahead, and the GPU. So that kernel is being executed on the GPU, and CPU is executing the next instruction, and it doesn't wait for GPU to print the hello world. I mean, GPU buffer to be dumped back to the CPU buffer and print the hello world. And in that, and due to this, you might see that that hello world from GPU is not printed on the CPU. And yeah, so the CPU is not waiting for the GPU. Both are executing asynchronously. And due to this, it happens in many cases. If you are lucky, you will see the hello world, but in many cases, it might happen that it won't even print the hello world, and the program would terminate. So to avoid this issue, we have this function CUDA device synchronize, which essentially tells the CPU that please wait until the kernel execution is finished, or I mean, so what will happen in this case is now kernel will be launched by CPU, it will move on, and it will wait for CUDA device synchronize here in this at this statement, and it will wait for all the GPU threads to finish, and once the buffer is dumped back, GPU buffer is dumped back to CPU, the things will be printed, and then the next instruction will be executed, which is return 0, and then the then the execution of mail will finish. So yeah, so if you take this program and compile it using NVCC and then run it out, you will be able to see the hello world, which is the correct output for this code. And yeah, so the key takeaway here is that CPU and GPU executes asynchronously, or they run asynchronously, and in some sense CPU needs to wait for the GPU kernel to finish, and for that we need this CUDA device synchronous, which essentially tells the CPU to wait until all the GPU threads are completed. Okay, so before moving on, I'd like to see if I missed any questions. Also, is it compulsory for global underscore and or we use global int or int? Yeah, so void and I guess I think you need to declare it with void only. You can't return value from kernel, but I need to check that. I'm not 100% sure about this. Okay, I'll take this question for offline and we'll post it or let you know by some email or something. So next question is, do we have to always call the kernel with 1,1 thread? No, I mean you can call the kernel with any number of threads. 1,1 is telling that you need to, I mean you are essentially launching it with one thread, but you can launch it with many threads. We'll see examples ahead. Yeah, there is some echo actually. I request everyone to mute unless you want to ask some question. Sir, how can we practice alongside? Any online ID or some setup needed on Earth? Okay, you can use, as I told in previous lecture, you can use Google Colab, or you can also use the GPU that's on your local machine, or you can use your computing facility available on our institute. But the thing is, you need to install NVCC. Otherwise, you won't be able to run the CUDA codes. At least those we are discussing in this lecture. Sir, why CPU and GPU runs asynchronously? So this is good question. Since CPU and GPU are different devices, so there is no synchronization between them. So CPU runs executes the instruction, and it offloads the chunk of computation which has to be done on GPU, and then it goes ahead. So it is not like CPU and GPU have some, they are not same device essentially. So computation is independent, and that's why they are executing asynchronously. Yeah, I hope that answers your question, Krishna. Sir, can we create multiple GPU functions? Yes, sure. Probably in next slide you will be seeing, not next slide, but yeah, in this lecture only we'll see like multiple GPU functions and call them at various instances in the main. Yes, you can completely do that. And doing so, do we have synchronized? Do we have synchronized them every time we call a new GPU function? Yeah, this is a very good question. We'll take this up in this lecture only. We'll see a couple of examples which will answer these questions. Okay, this demo lecture that you are talking about is already there. Probably I'll share the link to this demo lecture for Google Colab. You can go through that and let me know if you have any questions. Mostly you'll be able to learn everything from that video only. So yeah, I don't think that there will be any issue for using the Google Colab at least. Okay. Okay, so I'll move on. Okay, unless there is a question. Will this work with any hardware? My laptop doesn't have dedicated graphic card and uses an no. For this course, you will need to have the NVIDIA GPU. Intel graphic card won't work. So yeah, NVIDIA GPU is must for this course. Okay, so moving on. Sorry. Okay, so now we have I have twisted this HelloWorld program a bit, and let us see what will be the output of this program. And okay, let's consider this program, and I want each and every one of you to think what is the possible output of this program. And I'll wait here for a few seconds, and I request you to try this out and post your answer in chat. Okay, I am assuming that each and every one of you have tried at least. We have some answers here. 3 times hello world will get printed. Okay, hello world print statement within the kernel will be executed thrice. Okay, executed thrice. 6 hello world. Okay, 6 hello world. 6 times, 3 times hello world, and then on CPU. Yeah, that is okay. 3 times hello world. 3 times, then next line on CPU. Okay. Okay, good. I mean, you people are trying. That's good. I mean, okay. So I'll switch back to slides, and I request everyone to try. But okay, I'll switch to the explanation of that part. Okay, so we have 3 kernel calls, and so let's see how the execution, what is the execution flow for this program. So CPU will begin with main, and it will launch the first kernel, which is it will call the kernel first time using this call function call, and with one thread it will execute. So and then CPU will go on. Then it will launch the second kernel, then third kernel call, and so on. And then it will wait for then it will wait for CUDA device synchronize here. And okay, so when until and unless all these kernel calls are finished, CPU will wait here. So you should typically be able to see hello world, hello world, hello world printed 3 times, and then as all the kernel calls have finished its execution, CPU will move ahead, and it will then print on CPU, and then return 0 will be executed, and then we are at the end of the program. CPU has finished its execution of the code. So typical answer, so you will see a very deterministic answer for this code, which is 3 times hello world and then on CPU. Okay, so one key thing here to observe is that at CDS, CPU will wait as CDS uh, until each and every kernel call has finished. So it will never happen that on CPU will be printed before any of the hello world. So that is one point that you should note. And the second point that I would like to emphasize here is that there is something called as each and every kernel call will execute serially one after the another, because there is something called as a queue or stream inside which each and every kernel goes. So let me explain with this example. So CPU will launch this kernel, meaning it will load this kernel into something known as queue. Then it will move on, then it will load again this kernel into the queue, so and so on. And so what will happen is uh, queue is a FIFO data structure, so the kernel which is loaded first into the queue will be executed first by the GPU, and so on, and then the second kernel, and then the third kernel. So the order of the execution of this 3 kernel is also one after the another. So this kernel will be executed first by GPU, then this second, and then this third. So the key takeaway from this slide is kernel by default. So please remember, by default we can change this, but by default they are executed one after the another. And we'll see how to change this in the couple of later lectures. And second point that I already told you, that CPU launches all these 3 kernels, and then it moves ahead, and it waits at CUDA device synchronize. And it will wait here till all the kernels are finished. So as I told, on CPU will never get printed before this 3 hello world. So the answer is very deterministic, 3 hello worlds followed by on CPU. If you have any doubt on this, then I can take it on chat. Okay, I guess everyone is pointing it correctly. 3 times hello world and on CPU. Yes, correct. Sir, can you explain the function of CUDA device synchronize? Yeah, so it's essentially like some sort of a barrier. So it tells CPU to wait until all the GPU threads are finished. All the threads, GPU threads, all the kernel calls before it have finished. Sir, what is CDS? CDS is CUDA device synchronize. It's a abbreviation for CUDA device synchronize, CDS. Sir, what will be the output without CDS? Nice question. Actually, we saw that it might happen that there might be no output, as we saw in our first Hello World program. That CPU moves on and it doesn't wait for printing to happen. But yeah, we'll see some of the variations and probably you might get better idea of it. Can you explain 1 comma 1 again? What does the first and second one represent? Okay, so first one represents the number of blocks and second one represents the number of threads inside each block. There is something called as block inside. It's a way GPU threads are arranged. Take it that way, like there are blocks and inside each block there are a couple of, there are some number of threads. So let's say if you are writing 1 comma 10, then there is one block with 10 threads in that block. So yeah, so I think next question is 1 comma 12. Do we get 12 output from 12 thread? Yes, that is correct. We'll see that. I will get 12 outputs. 12 threads will print the same thing. Yeah. And this CUDA kernel's just instructions, or can we have a return value as we have in expressions? I didn't understand. Are this CUDA kernel just instruction, or we can have return values as we have in expressions? Yeah, so return value I'm not sure of. I haven't seen, at least as far as my experience is concerned, I haven't seen any kernel returning a value. But I need to check that out and I'll get back to you with it. I think someone else also asked the same question, like can we return the value from the kernel? So as of now, I am uncertain about that and I'll get back to you. Mostly answer is no, but I'll let you know. Okay, I guess I'm done with the questions. I'll get back to the slides and yeah, let's move on with some other variations of the Hello World. So this is the next program that we would like to study. And in this program, as you can see that there are two kernels. Again, we are launching just a kernel with just one thread. But this time we are printing, we have two separate kernels and we are printing Hello World 1 and Hello World 2. And we would like to know what is the output of this program. So I would like each and every one of you to try out, what can be the output, and post your answers in the chat. I'll wait for a couple of seconds here before I move on to the next question. Or next slide, sorry, not question. Okay, I'll move back to the chat to see what you people are trying. Hello World 1, Hello World 2 on CPU, Hello World 1, Hello World 2 on CPU. Good. Hello World 1, Hello World 2 on CPU. That is good. Both hello world will be printed on CPU. Oh, okay, hello world 1, hello world 2 on CPU. Okay. Okay, this is actually good. I mean, you people are at least trying. I like that. Yeah, source code.
Excuse me, sir.
Yeah, sorry, go ahead.
Sir, can you please explain again CPU and GPU concept? Actually, I was unable to attend the previous class, so that I'm not getting the things yet.
Okay, so actually, okay, let me put it in this way. Like, GPU is a separate device, and as I explained in this class itself, that in order to run anything on GPU, you need to add that global keyword, which marks that this function is a GPU function. And on GPU, you will be typically able to run the function using multiple number of threads. So thread is a think of it as a worker, and that function that we saw, that global, which was marked with that global, it will be run with the multiple number of threads, and you will be able to do the same I mean the instruction that are written in that function using multiple number of threads, and we'll see how we can get benefit out of it in terms of performance. And it's okay if you have missed the previous class. I think you'll be able to understand most of the today's lecture without most of the parts of today's lecture without uh, understanding the previous or knowledge of the previous lecture. But just in case you have any doubt apart from this, then you can ask.
Okay, sir. Got it.
Okay, I think, yeah, I'll place, I mean, I'll add this codes. Yeah, code part I'll probably add in that sheet only. And apart from that, yeah, I guess most of you have tried and most of you are also correct. One don't need GPU on PC as we can work on Colab, right? Sir, yes, that's completely fine. I mean, if you are able to run it on Colab, you don't need to have GPU on, I mean, on your personal machine. Okay, so I'm switching back to the slides. So let's try to understand this. As we are aware, like GPU will start from the main and it will launch the kernel one. That kernel one will go into the default stream or the default queue. So the kernel one will be loaded first in the queue. Kernel 2 will then be loaded because CPU will go ahead. It will not wait for the GPU to complete its execution. So kernel 1 will be loaded first in that queue, and kernel 2 will be loaded in that queue. And then CPU will wait that CUDA device synchronize for both the kernels to finish. And so like now as the kernels are executed in FIFO order, since they are pushed in queue, so kernel 1 will be executed first and it will print hello world 1. And please remember that this is happening on GPU. Whatever is written, I mean whatever functions are marked with global are executed on GPU. So actually this function is somewhat loaded in GPU and then it is like executed on the GPU. In the same way for the kernel 2 also. There is nothing related when, I mean, from execution point of view, this is completely happening on GPU. There is nothing related to CPU happening while executing this kernel. Similarly for this kernel 2. So hello world 1 and hello world 2 will be printed on GPU, and then as the both kernel calls are finished, I mean execution of both the kernels is finished, CPU will move ahead. I mean it was blocked here at CDS, CUDA device synchronize, waiting for both the kernels. So it will, okay, so both the kernels are finished. Hello 1 and hello world 1 and hello world 2 have been printed. It will move on and then on CPU will be printed by the CPU, because here at the main everything is being done by the CPU. So this part is completely, I mean, these instructions that are written in main are completely executed by CPU. So please keep a note of that. So printf on CPU is done by CPU and printed by CPU, and then we return and the execution finishes. So the output is hello world 1, hello world 2 followed by on CPU, and the output is deterministic. Please keep note of it. I mean, it will never happen that hello world 2 will be printed before hello world 1, because the kernels are loaded into the default stream or queue, and the execution is I mean, the way this kernel are taken for execution by GPU is in from the stream is in FIFO order. So first kernel will be taken, will be executed, then second kernel. So hello world 1 will always come first and then hello world 2. And since we have this CDS also, on CPU will also be printed later. It will never happen that output can be something else apart from hello world 1, hello world 2 and on CPU. Okay, so I think we are good with this this version of hello world. Now let's try this another version of hello world. In this case, I've just made a small change. I've just swapped this two line, this printf and this CUDA device synchronize. You can see from previous slide there is this change, and I want you people to try out this code. What will be the output for this code? Let us try and let's post your answers in the chat, and let's see how, and let's understand like how is it working. So I'll wait for few seconds here before I move on. I would like to see answers from you people.
Sir, the programming part will be right on CUDA compiler, right? We have to download it.
Yes, you need to download NVCC compiler.
But I'm using the Intel laptop here, so is it work on in this type of thing? Means, is there any issue regarding to this?
Okay, so with Intel, it will not work unless you have NVIDIA GPU. So inside your laptop, if there is an NVIDIA GPU, you will be able to
Yes.
run it. Okay, then you. Hello. If you have NVIDIA GPU, you will be able to run it. In case you don't have NVIDIA GPU, then also it's fine. You can run your code on something known as Google Colab, which is free. Free platform by Google. It provides free GPU time. You can try that out.
So we have to change the means in setting we have to change the GPU system, right? We have to change in the setting.
You are talking about Colab.
If we will use it in Colab.
Yes, you need to change the runtime to GPU instead of CPU.
Okay, fine. Thank you.
So can we run program in Kaggle also?
I'm not sure about it, but if anyone of you have tried and it's working, you can. I'm really not sure about whether Kaggle supports it or not.
Okay, sir.
If anyone have tried, then you can post it like what was your experience with it. I'm really not. I haven't tried with Kaggle. Okay, I guess let's move on to chat and see what was your response. We are okay. Hello world 2. Okay. Hello world 1 and hello world 2 will be printed on GPU and CPU. 2. Okay. On CPU, hello world 1, hello world 2. On CPU, then hello world 1, then hello world 2. On CPU, hello world 1, hello world 2. Okay. I guess you people are going in right direction. CPU will be printed on GPU. Okay. Synchronization might not be feasible for executing both in sequential order. on CPU, hello world 1, hello world 2. Okay, let's try understanding this code. Let's get back to slides. Okay, so again, like CPU will begin execution from main. It will launch dkernel1, dkernel2. Both this kernel will go in some queue, which is default queue, in FIFO order. So dkernel1 will be there, then dkernel2 will be there. Then CPU will move on and it will print on CPU. So, so in this case, the answer can be non-deterministic if you see, because CPU is not waiting before, CPU is not waiting for kernels to finish. It will print on CPU. It might print on CPU, okay. It might print on CPU before hello world 1 and hello world 2 are printed by GPU. It might also happen that if GPU finishes, GPU kernel execution finishes before, then in that case hello world 1 and hello world 2 might also be printed before, before the on CPU is printed. And it might also happen that hello world 1 is printed, then on CPU is printed, and then hello world 2 is printed. So any of three order is possible: on CPU, then hello world 1, then hello world 2. Then like that's the first one. Second case is hello world 1, then on CPU, then hello world 2. And the third case is hello world 1, hello world 2, and then on CPU. So these three cases are possible because CPU and GPU are executing asynchronously. And again, one point that I'll reiterate here is that it will never happen that hello world 2 is printed before hello world 1 because of that default stream or queue which we have which is maintained between CPU and GPU. And second thing is, it will never happen that hello world 1 and hello world 2 are never printed because we have this CUDA device synchronized. So CPU will at least wait for both these kernels to finish. It will not happen that it will finish execution and it will not, wait for buffer printing and all those things. So it will never happen that this hello world 1 and hello world 2 will not be printed. So they will be printed. And three possible answers of this, three possible orders that are possible are the one that I earlier told you. And yes, that's the output of this program. So I hope that any one of you, most of you got it, or every one of you got it. If there are questions, what if we don't write CDS function in the last program? Will it be in the queue still? If not one can be overwritten. Okay, so if we don't write CDS, then it might happen that only on CPU is printed, and then CPU doesn't wait for the GPU buffer to pushed back, and it just finishes its execution. So in that case, it might happen that only on CPU is printed and no hello world 1 and hello world 2 is printed. It might happen, but if you are lucky, it might also happen that both of them are printed. What is the final output? I told you that there are three possible outputs, but mostly you will see that on CPU is printed first, then hello world 1 and then hello world 2. There is a reason behind it, because CPU is much faster because it just launches the kernel and then moves ahead. It does not wait. It's not waiting. It's just executing instructions in order very quickly, and yeah, that's the reason. Okay, sir, what is the purpose of writing CUDA device synchronize? I explained you earlier, right? CUDA device synchronize is something like a barrier. Writing CUDA device synchronize ensures that CPU will wait for all the kernels that are written before it to finish its execution. If we are doing 1, 2 in D kernel, there are 2 threads, right? So each thread will do the same block once, right? Okay, if you are writing 1, 2, then it will happen that that kernel will be executed by each thread. That kernel will be executed actually by each thread. So you will see that hello world is printed twice, but we will come to it, don't worry. Sir, can you please run a program in Google Colab? Okay, I think okay, I'll see this from next lecture onwards, but for right now I think I need to load everything on Google Colab, and I think it will take very long time. Probably will overshoot the lecture time. Yeah, sir, is nested function concept applicable for kernel? Yes, nested function concept is applicable for kernel. And yeah, I mean, probably we won't be covering this in this, I mean, covering that concept in this course, but yeah, this concept is definitely there. So you can call a kernel from one kernel. In fact, there is some another keyword other than global, which is called as device keyword, using which you can call. So once you are there in uh, global, which is a kernel, global function, which is a kernel, you can call a device kernel, which will also be executing on GPU. So yeah, there is definitely nesting there, and yeah, in that case, will it still follow the queue concept? Uh, yes, it will still go in that queue only. Queue concept will definitely be there. So this queue concept is known as stream. So everything, I mean, each kernel uh, is loaded in stream, and the GPU picks up that kernel for execution from that stream. It is also known as, I mean, queue, which is first in, first out ordering. Okay, I think I have answered almost all. Yeah. The questions. So let's get back to the slides. Sorry. Uh, your voice is very feeble. I am unable to hear you.
Yeah, are you able to hear me now?
Yes, please go ahead. Yeah.
You said there are three possibilities. One is the first, the on CPU, and then HelloWorld 1, HelloWorld 2. The other one is can be this HelloWorld 1, 2, and then on CPU. What is the third one you said? What third
Okay,
possibility?
so third one is like Hello World 1, Hello World 2, and then on CPU last. Because it might happen that CPU is very, I mean, CPU takes a lot of time executing next statement, and let's say GPU kernel launched and finished executing
Yeah, that is one
that
of the
step.
possibility that I have told. What is the other
Okay.
possibility you said?
Okay, so if that's already covered, then this
There
one
are
on
three
CPU.
possibilities, right?
Yeah.
You said.
Okay, I'll type it in chat. Probably then we might be able to on CPU H1, sorry, H1 and then H2. This is the first one. Second one is H1, then on CPU, then H2. That is second. And the third one is H1, H1 on H1, H2, and on CPU.
Okay.
So these are the three possibilities that we can. But
Okay.
mostly you will be seeing the first one on CPU, H1 and H2, because
Right.
generally CPU is very fast. I mean, it launches. Launches meaning it pushes the queue in the that stream or that queue, and it moves on very quickly.
Okay.
And
Okay.
it doesn't wait for kernel to finish unless we have placed that CDS CUDA device synchronize.
Okay. Got it. Thank you.
Okay, then I'll move back to the slides. Okay, so we saw this, and yet, I mean, there is one more program that we would like to analyze. So I would like each and every one of you to try out this program, and also check which printfs can be executed in parallel. I'll wait here for a few seconds so that you people can try. Okay, I'm hoping that each and every one of you are trying. So let me move back to the chat. Okay, okay, there are a couple of responses. Yeah, CUDA toolkit you can install. Okay, so CPU 1, CPU 2, CPU 3, Hello World 1. I mean Hello World, Hello World, Hello World on CPU. Okay, Hello World CPU, Hello World CPU 1, CPU. CPU 1, CPU 2, CPU 3 can execute in parallel. Mhm. Okay. I guess most of you are getting the same answer, and that's correct actually. Okay. 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 Printf statement with kernel and printf statement function. Yeah, that is actually correct. Printf statement with kernel and printf statement in the main function will be executed in kernel. Yeah, this is correct. Yes, we will get different output. Yeah, this is the precise answer. Sorry, yeah, sure. I'll show the code again. Yeah, so for a couple of seconds, I'll wait so that each and every one of you can try out this code. Okay, I'm now assuming that most of you might have tried it, or at least thought about how, I mean, what will be the execution flow and which printfs can execute in parallel, and what are the different possibilities, I mean, what are the different possible answers that can arise out of this code. Uh, let me go back to the chat once. That is right. Other possibilities as well if we did more load on CPU. That's correct. Correct. CPU 1, 2, and 3 all will be printed together. Okay. Okay. So let's understand this code. Okay. So again, CPU will start executing from main. First kernel will be launched. It will be loaded in the default queue, and then CPU will move on, and then CPU 1 will be printed. Again, second kernel will be launched and it will be loaded in the queue. So queue already has kernel 1, then it I mean first kernel, then the second kernel will be loaded, then CPU 2 will be this CPU 2 will be printed by the CPU, and third kernel will be launched by CPU. So again it will go in that default queue, and then CPU 3 will be printed, and then CPU will wait here at CUDA device synchronous. Now these three kernels are in the stream or the default queue. So one by one execution of this kernel will happen, and you will see that there is after all these three kernels are executed, hello world, hello world, hello world, hello world will be printed. And once that is finished, CPU was waiting here at CDS. Since all these 3 kernels have finished execution, it will move on and then will print on CPU. So one of the possible order is CPU1, CPU2, CPU3 followed by 3 hello worlds and then on CPU. That is just one possible order. But again, different scenario can arise. Let's say CPU had launched the first kernel. It went into, it went printing CPU1. Let's say before that, this kernel, first kernel launch, finished its execution and it printed hello world. So this can also happen. So hello world can be printed, then CPU1, then again hello world can be printed, then CPU2, then hello world, third hello world will be printed, and then CPU3, and then on CPU will be printed. So this is also one possible order. So key thing to observe here is that this 3 kernel launches can happen. This not launches, this 3 kernel execution, this one, and this one can happen in parallel with this 3 printfs of CPU. So this, in fact, coming back to our question, which printfs can execute in parallel? So the answer is the 3 hello worlds which will be printed by GPU can execute in parallel with CPU1, CPU2, CPU3, which is printed by CPU. So you will see any interleaving. You can expect to see any interleaving of these 3 hello world and CPU1, CPU2, CPU3. But as I told earlier, mostly you will see this output CPU1, CPU2, CPU3 followed by 3 hello worlds, then on CPU. The reason is that the CPU is much faster. It just launches the kernel and then moves on before even the any of the kernels have finished its execution and the write buffer is brought back to the CPU. So that's one thing, which so that's the answer to which printfs can execute in parallel. One more point that I wanted to note here is that on CPU will never come before any of the printfs. Any of the 3 hello world printfs and this 3 printfs of CPU1, CPU2, CPU3, because we have this CUDA device synchronized here. So CPU will wait for all these 3 kernels to finish, as well as due to sequential execution on CPU, it will also wait for this 3 prints. Not wait, it will execute these 3 prints and then only it will move on to next print. So on CPU will always come after all the printfs that are there in this program. So you will never see on CPU coming before any of the printf. So that's the second point that I wanted to make. So if any one of you have any doubts on this code, then please feel free to post right on the chat. I'll take them up. Yes, that is correct actually. Yeah, that's precisely. On CPU will be the last. The remaining depends on the load. That's correct. Yeah, perfect. Any questions? Please feel free to post on the chat. Otherwise, I'll move on. Okay, so there can be multiple final outputs, Aditya. I talked about few of them. And most probable output is this CPU1, CPU2, CPU3 followed by 3 hello worlds and then on CPU. That's the most likely case. Okay, if there are no questions, I'll move ahead. We have a few other things to cover. Okay, so these 3 questions you need to check offline. Where NVCC is installed on your system. So in Linux, you can try which command, which NVCC, and you will get the location where the NVCC is installed. And then you can check the CUDA version using NVCC ---- version in Linux. And third thing is you can check what this device query is, and you can learn more about it. What is it, and what's basically the use of it, and all those things. So this 3 things, please try offline. Yeah, it's coming yeah, so going to next slide. Okay, so I guess couple of you earlier pointed out this thing. Let's say we want to, I mean, we were just running Hello World on GPU, but just using just one thread, and yeah, that was not quite, I mean, that was not doing it in parallel. I mean, just one thread was working. So we want to see, like, I mean, how can we execute this Hello World multiple times using multiple threads? So it's quite simple. We just need to change one thing, which is the number of threads, and we know how, I mean, as I explained, we know how to do it, because the two parameters here that we are passing to kernel is denoting the number of threads with which we are launching the kernel. So 1 comma 32, if we write this, then it denotes that we want to launch the kernel with a single block and with 32 threads inside that block. So if we launch this kernel with this configuration, then when the kernel is, when the kernel execution begins, there will be 32 threads which will be executing this single piece of code, which is this t kernel function, which will be executed on GPU by 32 threads, and CPU after launching this kernel will wait here for all the threads to finish. So all the threads will print this hello world independently, and the output of this program will be hello world printed 32 times, one time by each thread. And then then CPU will, each threads have finished execution, CPU will go ahead and will return 0 and will finish the execution. So output will, so if we compile it using NVCC and run it out, we'll see that hello world is printed 32 times. And okay, so the key point to observe here is that we can change the number of threads using these two parameters. First is this first parameter, which denotes the number of blocks, and then second parameter, which denotes number of threads in each block. Okay, so moving on. So there are this few parallel programming concepts which I would like to highlight before we move on. First thing is process. So the formal definition is the process is the program under execution. But more practically, let's say, I want to understand what the process is. Then let's understand it with an example. Let's say you have C program. Now let's say you compile it. You compile that C program, and it will be in the secondary storage or on your disk. But when you run /a.out, that program will be loaded into the main memory or the DRAM of your system, and at that time that program becomes process, because that binary file is loaded in the DRAM of the computer, as well as the other data structures will be associated with it for the sake of its execution. Let's say it will be allocated a heap for dynamic allocation of the memory, because you might declare some memory using malloc or something inside your code, and for that you need space. To allocate a variable, you need a space. So for that, heap will be allocated. Heap will be allocated to your process, which is your so that process is a collection of multiple things. One is that binary, another is heap, and then you might also declare some variable statically for using, like, let's say for example you declare int a. So such allocation of a variable will be done on stack. So for that you need something called a stack. So inside process there is a this binary, then stack, then heap. Then you need to also take care of like what is the current stage of execution, where I'm currently, which instruction I'm currently executing. For that you need program counter and so on. So one process might have multiple things, and yeah, so each, so one process will have multiple things, and it will be private to that process. And the examples of the process are Notepad, Chrome, Word is also a process. And so whenever you click on your Chrome, when you launch your Chrome, it will be loaded in the main memory, and it will be allocated all this stack, heap, and all those things for its execution for its execution. So yeah, that's it. And next term is thread. Thread is, technically, if technical definition is, it's a lightweight process. But I mean, let's understand it practically. So let's say you have this word, which I told is a process. Word is a process. Now, what can be a thread inside that word? Word is a process, right? So each process might have multiple threads inside it. And let's say if a word is a process, then thread can be something like a spell checker inside that word. Because let's say you're typing and there might be something like you write it wrongly, I mean wrong spelling or something, and it will autocorrect it. So that's one thread which is working inside that process known as word. Uh, and it is working, I mean, independently, and there might be several other threads also which are doing different things. So I mean, what's the difference between thread and process? First of all, thread is a part of process, so each process might have multiple number of threads. But why it is called lightweight process? The reason is that threads have multiple things in sharing. For example, the threads share the code part. So binary file that is loaded is shared among all the threads. Then there is heap, which is also shared among all the threads. But okay, so there are multiple things that are shared, but there are also a couple of things that are private to each thread. For example, stack is private for each thread. Then there are several registers which are privately allocated to each thread. Then as each thread is executing independently, it also needs its own separate copy of program counter. So all these things will be private to the thread, but there are multiple things that are shared, like file systems will also be shared shared among all the threads. So since multiple things are shared, it is known as a lightweight process. Okay, so that's a bit about thread. But then coming to operating system. So think of operating system as a manager. So you want to be able to talk with hardware directly, at least, I mean, for the high level machines that we have nowadays. So for that, you need something like someone like manager who talks on your behalf to hardware. And let's say you want to print something on the screen. Then for that, you need to invoke a system call like write, and that write system call will instruct the hardware to. So write system call is written inside the OS, and that system call will tell the hardware to print something on screen. So for each and every for each and every thing we have to, for each and every functionality of the hardware, we need to talk with OS, and it's kind of a software that manages the hardware, and it's also the software with which the user interacts. And there are multiple examples of OS like Windows, Android, Linux, even Mac OS is the example. The fourth thing is the hardware components itself, like cache. Cache is a very small memory which is close to the processor. And advantage of having such a small memory is that access to this is very quick because it's very small. The size is small, so indexing it is very fast. But there is disadvantage that its size is small, so you won't be able to store many things inside it. But whatever you can store inside it, the access will be very fast, and processor can get it with very less latency. Then comes the main memory, which is slightly below the hierarchy, below in the hierarchy as compared to the cache. So main memory, so nowadays main size of the main memory is, as you people know, like 8 GB, 16 GB is normal for the normal computers. While for cache, you might see that size are just in few MBs, like 256 MB or something like that. Not okay. So that's the difference. But yeah, the main memory can handle, can load a large amount of data in it. And if the data is not present in cache, then processor or core will go into the main memory. And then comes the core. Core is actually the hardware component on which the thread runs, and there is this concept that thread can jump from one core to another core, which means that if let's say we have two threads per let's say there are two threads allocated to one core, and let's say that thread number one is currently being executed by the it's currently running on the processor one, and let's say there are 5 processors, and let's say it happens that thread 1 needs an IO, then it will go for IO, and processor 1 will pick the thread 2 which was allocated, scheduled on it, and starts running it. By the time, let's say, thread 1 have finished its IO, and it wants the processor again, but processor 1 is busy, so it might go to some other processor which is processor number, let's say 4. In that case, we can say that thread 1 has jumped from processor number 1 to 4. So that is something called as thread jumping of thread. And yeah, so I'll probably stop here for questions because I think I spoke a lot. I'll see if there are doubts, if any. CPU 1, 2, and 3 all will be printed together. Okay, I guess this is for last CPU. Okay, yeah. Okay, I mean, you don't need to submit the homework. You just need to try offline. I mean, just try it on your own. You don't need to submit it anywhere. Does the complexity of program determines the number of threads being allocated? No, actually, the number of threads that will be allocated. No, I mean, it's the programmer who decides the number of thread with which the kernel is launched in our case for CUDA codes. So let's say the code might be very simple, but let's say you want to launch it with lots of threads, then it's possible. I mean, no one, I mean, at least not CUDA will not stop you. NVCC will not stop you from doing that. And do we always have to manually assign the number of threads, or is there some way we can make it automatic? I think you need to manually allocate the number of threads. The college notebook supports CPP syntax, or does it use Python syntax? Okay, Colab. As far as I mean, I am acquainted with CPP syntax. I am not aware with Python syntax as of now, but I think it might be supported because Jupyter Notebook supports Python, and I think it should be supported. But someone of you have to check that. CPP is definitely supported because I have tried multiple codes on Colab with CPP syntax, so that won't be an issue. Python you have to check. Based on what factor we can choose number of cores. Number of cores are fixed. You won't be able to. I mean, number of cores are there in hardware. So let's say, for example, your GPU has 5,000 cores. That you won't be able to change, but the number of cores are determined based on the type of the hardware. So GPU has very large number of cores, while CPU has only few tens of cores. So yeah, that's it. I think I answered your question, or I misunderstood it. I don't know, but you can unmute and ask if I probably missed something. Okay, so thread jumping is okay. I'll reiterate it. So let's say there are two processors. Just take it in that way. There are two processors, P1 and P2, and processor 1 has been allotted two threads, which is thread 1 and thread 2. Now let's say, okay, so at one instance only one thread can execute on particular processor. So processor 1 was executing thread 1 and thread 2 was in the queue. Now let's say processor 1, which was executing thread 1, and thread 1 needed to go for IO, which is input output operation. So it went for that input output operation, and the processor 1 was idle, it was not doing anything. So what it did was it took the thread number 2 for execution. So now let's say thread 2 was executing on processor 1 and thread 1 was in IO. It finished at IO and it again needed to do some computation on using that processor. But processor 1 is busy. It is busy with the thread 2. So what thread 1 did was it went to processor 2 and started executing on it. So if you get it correctly, then initially thread 1 was with processor 1, but after IO it went to processor 2. So it actually jumped from processor 1 to processor 2, and that's typical thread jumping that happens in CPU as well as on GPU. This is a very common thing that happens. Sorry for that noise. Yeah, I hope that you understood it, Clifford. Yeah. Hello. Okay. I'll switch back to the slides. Okay, so there is this one more code that I would like you people to try. Try writing the CUDA code corresponding to this CPU code. So I'll wait here for a few seconds and I will like all of you to try out this code. Please, please write the CUDA code corresponding to this C code. Okay, one thing that we need to ensure that we need this computation part, which is 0 to n, which is essentially printing the squares, to be done on GPU. This part we need to do it on GPU. How can we do that? Once you are done, please post your answer on chat so that we can discuss. Yeah, please feel free to. Okay, I'll wait for a few seconds more before I switch back to the chat. Okay, I'll go to the chat and see what you people have done. So can you share the slides before the start of the class? Okay. Okay, then I'll do that. I'll just add those slides in that sheet that we are maintaining. And before each class, I'll just add a link to that slide in that corresponding lecture column or row. Sorry. And okay, next question is, do we just add it to the kernel? Yeah, that is one possibility. That one thing that you can definitely do. You can directly add it to the kernel. Asynchronous to the IO, define the kernel with printf and then print using n threads. Yes, that is another possibility. We can print it with n threads. But one thing that you might need, like, how can we do it with n threads independently? Like, thread 1 is printing the 0 square and thread 2 is printing the 1 square and so on. That we need to take care, which we actually will see. Yeah, so this is important point. Can we create a kernel which takes input as I and prints I into I? Yeah, we'll see how to do it. Yeah, that I needs to be taken care. You are correct. Yes, this is one possible way. This is correct. Rushikesh, yes, this is the one of the possible way in which we can do. Okay. Where square is equals to I into I, print square. Okay. Yeah, so you are trying to pass that parameter, that is parameter, I guess. This is also possible, but we need to check if it is. I think there will be some compilation issues because of I into I think you are. You are launching thread I into I threads. No, I don't think. Yeah, this we need to change this code a bit. This Joshua. Yeah, we'll need to change this code a bit. It won't give correct answer. Okay. Anyways, I'll switch back to the slide and we'll see how to do it. Yeah, we have a couple of minutes. We'll finish this thing and then we'll stop. Okay, so one of the way in which this can be done is very simple. I mean, we can just launch the kernel with one thread and can place this loop inside the kernel. And yeah, this will print correct answer uh, as it was with CPU. But there is one problem that it is running entirely sequential. I mean, in an entire sequential manner. There is no parallel thing involved here. There is one thread which is executing. I mean, this for loop in a sequential manner, and yeah, we are printing I into I, but there is no parallelism involved. So my next question is, how can we make this parallel? And to make this parallel, we need to get hold of something called as thread ID.
Sir, hello.
Yeah, please go ahead.
So can we pass parameters to this GPU function?
Yes, yes, you can pass. So let's say, let's take this fun kernel launch. Inside this braces, you can pass the parameters.
So instead of doing this sequentially, can we start for loop in the main function and passing I value from 1 to 100 maybe?
Yes, that is also one possible way in which you can do. You can pass that I value by launching the kernel in the loop, and then yeah, that kernel will print the I into I. But still, that will involve I mean, that will involve launching one thread for each print, right? And that's also very high overhead. And still, we are not doing things in parallel because one kernel launch is there for each squaring operation that we want to print, right? So let's see how can we do it in better way. So this is one of the better way in which we can do it. We can launch the kernel with n threads, where n is the number till which we want to print the squares. And uh, inside this kernel, inside this kernel, we need something to identify a thread. So this statement thread ID x.x will give the ID of a particular thread. So let's say we are executing this kernel with n threads, then first thread, when it will see this thread ID x.x, it knows that my ID is 0. So thread number 0 has ID 0, thread number 1 has ID 1, and so on till 99. Since there are 100 threads, their ID will be from 0 to 99. And what each thread will do is, based on their ID, it will print its square. So thread 0 will print 0 into 0 square, thread 1 will print 1 into 1, which is 1 square, uh, and so on till 100, till 99, which will be done by 99, the thread which has 99 as its ID. And after all of this is done, I mean, CPU was waiting here for CUDA device synchronize. And after all of this is done, after all this printfs are done from GPU, CPU will move on and execution will finish. So one cool thing to note here is that there is no loop involved here. Everything is, everything is done by each thread in a very parallel manner. But there is still one problem with this code, and that problem is that output of CPU and GPU might not match, because each thread is executing in a very asynchronous manner, and you might see that output might be jumbled. And yeah, this is the issue that we face in multi-threaded execution. But as long as you are not concerned about the correctness, we'll be able to see all the squares, but in jumbled order. So that is one issue that is with this code. And yeah, I think with this I'll stop here, since we have already overshot the time. It's 6:30. But if anyone of you have any question, then I'll be very happy to take them.